All right, you guys, we're going to talk about density curves and the normal distribution. All right. Sometimes the pattern of a large number of observations is so regular we can describe it by a smooth curve. I would write this down. For something to be a density curve, these two things have to be true. All right, one, it's always on or above the horizontal axes, the x-axis, okay? And the area has to be exactly equal to 1 for it to be a density curve, okay? So the area is on the x-axis, or the curve is above or on it, and the area is exactly 1 underneath. Okay, real data will not be perfect, but we will estimate because that's what we do in stats, okay? So you might see a curve like this. This is a density curve right here, even though it makes a rectangle, because it is on or above the x-axis. And the area, if you do from here to here, this is a distance of 4. This is a distance of 0.25. So if you just did base times height for a rectangle, what is the area of that rectangle? 1. So it is a density curve. Okay. And this one over here, same thing. So if we have on or above the x-axis, we're good to go. And the overall area of this curve is 1. All right. A normal distribution. So we have density curves, which could be rectangles. Okay, they could be other shapes, all kinds of shapes, right? But a normal distribution we're going to do a lot with in this class. Okay, a normal distribution is bell-shaped and symmetric. All right, if you see this notation where you have a capital N and maybe the mean height of women is 65 inches, okay, with a standard deviation of about 2 inches. If you see anything written like this in your book, this means it is normally distributed. And the mean is always listed first, and the standard deviation is always listed second. So mean, and then standard deviation. Okay, curves with larger standard deviations are more spread out. So you might have a curve that does not go quite as high, all right, or more spread. That just means it has a larger standard deviation. What's really cool about the normal curve is we can figure out the percent of data that falls within 1, 2, and 3 standard deviations. So first of all, according to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and standard deviation of 8. Sketch the distribution. Label the mean and the points 1, 2, and 3 standard deviations above the mean. So draw yourself like a normal curve, roughly, like this. And the mean always goes in the middle. So it says that the mean of these 12-year-old boys' heights is 149 centimeters. Okay, and you are always going to split your curve into thirds. So we're going to go 1, 2, 3 standard deviations above the mean, and 1, 2, 3 below the mean. So a boy who is at 1 standard deviation above the mean, we would add 8 inches because it says that his standard deviation, their typical distance from the mean, is centimeters. So I'm going to add 8 to this to get 157. And then I'm going to add another 8. If there are 2 standard deviations above the mean, that would be 165 centimeters. And then I'm going to add another 8, and that would be 173 centimeters. And if I go the other direction, so if you're 1 below the mean, that would be 141. All right, and then I'm going to subtract another 8, that'd be 133. And I'm going to subtract another 8, and that would be 125 centimeters. All right, so the mean goes in the middle, You're always going to add the standard deviation 3 times and subtract the standard deviation 3 times. All right, this is called the empirical rule. You will learn this in AP Psych. Anyone in AP Psych? All right, so you'll be doing this in AP Psych as well. All right. Now, if the curve is normal, so this is only for a normal distribution or an approximately normal, it's fine, okay? 68% of the data always falls within 1 standard deviation of the mean, okay? And then 95% of the data falls within 2 standard deviations of the mean. So a whole lot of the data falls within 2 standard deviations of the mean, all right? So if you're like above 3 standard deviations above the mean in height, you're like rare. Okay, it doesn't happen often. All right, and then 3 standard deviations above and below is 99.7% of the data. Now, we can find every little piece of this graph, and I actually recommend filling it all in right now, and it'll make this worksheet super easy. All right, so again, 1 standard deviation above and below is 68% of the data. How much then is here to here and here to here? 34% of the data, right? And 34%. I'm just going to break down the whole thing, okay? Now, 2 standard deviations. So if I go to -2 and I go to +2, all right, 95% of the data always falls from here to here. What if I just want this area right here? Can anyone tell me how I would find just that area of the graph, percentage-wise? What do you think? You could do that. I'm going to do this. 95 minus 68. So I'm taking all of the area from here to here is 95. And then I'm going to subtract out the 68. And I'm going to divide by 2. Okay. So I take the 2 standard deviations, 95, minus the 1, and I divide by 2 because I just want this piece. And that gives me 13.5%. And then this is 13.5%. So 34, 34, and 13.5, 13.5 should add to 95. Okay. Now, I want to go 3 standard deviations. So I have a -3 and a +3. What if I want this piece right here between 2 and 3 standard deviations? Raise your hand if you can tell me how to find that tiny little area there. What do you think, Keith? And that is going to be actually correct for this tiny tail there. You're close. Anyone have a thought? Yes. Yep. Yep. 99.7. 99.7 is all of this area in here, right? Minus 95 divided by 2. Okay, when you do that, you get 2.35% for each of those little areas there to there, okay? And then we need the teeny tiny little tails, which means you're either really, really small or you're really, really tall if you're in those areas, if we're talking about height, okay? The whole entire curve is what percent? 100 minus the 99.7 divided by 2, and this would give me 0.15%. Okay, 0.15%. Then they would add all the way up to 100. Okay, now that we know those, we can answer some questions. All right, so here is my same 12-year-old boy's example where 149 is in the middle. They're going to ask us questions based on these standard deviations, okay? What percent of 12-year-old boys will be over 133 inches tall? I would like you to draw the curve, okay? Again, this is the little it's dragging, right? And we're going to add, do this, okay, greater than 133. There are a lot of ways to find this. Does anyone want to give me one method to find the percent of boys who are over 133 centimeters tall? Something was not participating in that. Yes. Yep. And we just learned that this little piece here is 2.35, and this little piece here is 0.15. So that totals 2.5%. And do 100 minus 2.5%, and I get 97.5%. Okay, that would be one way to do it. All right, what percentage of 12-year-old boys are between 133 and 141? So again, you'd put your 149 in the middle, and you'd add 8, and you'd subtract 8. Now I want from 133 to 141. This is from the second to the third standard deviation. We could just look right here, right? Or if you memorized the 68 and 95, do 95 minus 68 divided by 2, right? And I get 13.5% of boys are in that lovely range of height. All right, now we're going to switch to young women, and now we're in inches. So 64.5 is the mean. This is the first number. It's always the mean. And that second number is the standard deviation, so I add 2.5 inches 3 times, and I subtract it 3 times, right? So that's just sketching the normal curve. Then it says what percent of young women have heights greater than 67 inches. Anyone want to tell me how to do this one? How much of the data falls here? Okay. How much falls here? Ooh. What's happening? Malicious activity. Oh my goodness. Cool. All right. 2.35. Someone's stealing all my stats. All right. And we would add all those up, right? And we'd get about 16%. Okay. What percent of young women have heights between 62 and 72 inches? So again, from 62 to 72, let's see where that falls. So I have 62 to 72. All right, how much of the data goes right here? Okay, how much goes right here? And how much right here? Okay, add those up. Whatever that is, okay? All right, you guys. Another thing that they might do is they might ask you, is this data roughly normal? All right, is this data roughly normal? We're going to learn a ton of ways to check for normality in this class, but one way is to say to yourself, does this follow the 68, 95, 99.7 rule? And it doesn't have to be that close, just ish, okay? And if it does ish, you're good to go. I can just look at that data and say it's pretty symmetric, right? But we could actually check and see percentage-wise. If this is the mean and this is the standard deviation, first I can do the mean plus 1 standard deviation and the mean minus 1 standard deviation, okay? And if I add the mean plus 1, I get 11. And if I subtract this minus 1 standard deviation, I get 5.4. So I want to know how much of the data falls from here to here. All right, although I think 11 is actually here. I don't know where this is marked. Anyways, okay, you can count up all of these dots out of the total dots, and you would get 23 out of 32, about 72%, okay? Now I want to do 2 standard deviations. So this time I would do 8.2 plus 2.8 plus 2.8. That's 2 above the mean. And then 8.2 minus the standard deviation minus standard deviation, that's 2.6. Figure out how much of the data falls within 2 standard deviations of the mean. It's 94%. And then on the third one, we would add another 2.8 and subtract another 2.8, and that is 100% of the data right there. And you would be like, you know what? That follows the empirical rule pretty well, because we can be flexible, okay? All right. So that is one way to check for normality. All right, you guys, grab this lovely worksheet 2.2a and see if you can find the percent of scores that fall exactly on a standard deviation.